So welcome everyone to today's session. So today's session, our topic is the first common issue that we face when we do regression analysis. Okay, that first common issue is called heteroskedasticity. So this is the first issue that we have to cater when we are estimating any model. Reason behind is that we are discussing its background right now. So the model that we already discussed is OLS. We have already learned how to do it in R. We have already learned how to do it in SPSS and also in Excel. So there are three ways we studied this model in the previous sessions. So OLS is a model that OLS is actually an algorithm that does the least square function to solve unknown alpha and beta. So it can solve us unknown alpha and beta by minimizing square of residuals. So what this method, so OLS, then whenever you see that somebody has written that he has done OLS, that that means that OLS is a method that is used by softwares to minimize the residuals to calculate alpha and beta. This function is important because if we have a bigger data, we cannot use the simple mathematics rules to solve alpha and beta manually. So this was but this OLS has many assumptions that we discussed previously. So there are several that are affecting the way they're affecting the results. So if they are not there, if any of the assumption is failed, the OLS will not give you the best results. So you already discussed many of them. So today we focus on one of them and go into detail that how it comes, what is the reason why behind its evolution, and how to solve it. Okay, so we'll start with the background. So the OLS model that we did was it is based upon data of similar objects. Consider that you are trying to estimate a model on on the time on the model. Consider that you're trying to estimate a model on the estimated life of a bulb. Okay, so when you're making this model, since the bulb do not have any thinking ability, or the bulb do not have any ability to change its behavior, or the bulb do not have any ability or what you call is consciousness. It doesn't have self consciousness, so it does not know in reality that why when we do this model of estimated life of a bulb, it will not create any change in the way bulb is working throughout its life. Why? Because it's not a human being. But the problem with so it means it will not deviate its performance. Okay. Secondly, since it's a technology based item, all bulbs are alike. They are similar to each other. So their dispersion in types in type is very small. So because even if you see difference in the quality of a bulb, their dispersion means their difference in the types is not very big. So it means when you estimate a model, overlays will work fine because you don't have to consider that bulbs could be different from each other. So the estimating model will perform sweetly, as this saw in the as we saw in the theory, that OLS will give you estimates and it has this advantage, this and that. But the problem is when we estimate a model of anything else, suppose determinants of profit of banks. The problem with this is that here you written bank as it is some object. But the problem is this object is not very small as compared to a bulb. It has several subunits. It has a governing body, and it has consciousness. What does it mean by that is that banks are dynamic in nature as compared to a bulb. So banks will behave differently for different environments or for different situations. So it means they will be a large heterogeneity in the way banks perform. The reasons can be many. So first reason can be because of the size differences. Large banks might perform differently than the small banks. Second can be because of the what you call it, the domestic versus foreign banks. So that's why there are differences. Other can be Islamic versus conventional banks, or what you call it. Other differences are public versus private banks. So there are many subgroups that exist within the nature of the bank. So when you say determinants of profit of bank and you group all of the banks together, what does happen is that it assumes that they are all alike, and it tries to fit a model where you have some specific independent variable and some profitability variable as a dependent variable. But what it is missing is that you have not incorporated the subgroups that exist within the group, within the overall sample of a bank. And and the reason is that if, let me make a book, if the subgroups perform differently, it will start to create a problem. Why? Because initially we said that they are same and they will be perform in the same way. But if they are different, there are some different subgroups. What will happen? That it will lead to different outcomes, and the regression is trying to give us one outcome, but in reality there are more than one outcomes. So what will happen? So let's go to the next diagram. Now I will try to give you some diagrammatic reason. So we have a y-axis and an x-axis, and let's say that We have here some independent variable, let's call it leverage, and we have ROA as profitability. So let's say the more leverage is more profit. Okay. So logically, theoretically, it every firm will have this logic. But the problem is that when you say that it is positive, theoretically it is correct. But the problem is if you have some subgroups which have a different issue. So, for example, one of the set of the banks which are Islamic banks might have uh, lesser positive sign, maybe because of the fact that they are asset based, so it takes time for the asset to perform. So for the specific time period it is too small, so the data is actually cross sectional, and the time period that you selected are very few years, so they are not able to get returns from short run. So it means that actually the sample has two subgroups, one is Islamic and other is non-Islamic. So one has a higher positive effect. So let's call it Islamic and others. So when you estimated both together, so regression gave an average. Okay, so the regression will not regression does not have any consciousness to see what is the subgroups type, so it will consider data as a homogeneous unit. It will give us an average, but the problem with this is that suppose when you try to estimate the data, so the dots that are placed in a sample will be look like this. And regression, what will you do is it will start the line from the middle, and it looks very fine. The red line is in the middle of these crosses. The crosses are what the joint incidence of two variables. It's a scatter plot. So when you observe these dots without this green and blue line, you notice that the red line is actually in the middle. So red line is observed to be a good fit, because apparently it is in the middle. But the problem is that when you start to estimate when you start to predict the model, what will happen is it tend to have higher errors, because the dots are actually not on the line, they are away from the line, but the line is luckily in the middle. And why it's in the middle? Because regression tries to fit a line which is starting crossing from the center of each dot. So by construction it is luckily, or by construction it is at the correct position. But problem is in real life, there are two sub models. There's on this model and this model, and these dots are actually crossing from the middle. Let's assume that there are a few more dots, so that this line is also complete. So there are a few more dots here. So this way, the good fit is looks correct, but when you estimate the model, you will notice that it has high errors. So and you also notice that the lines are deviating. So if I take a black color, the distance between the opposite banks were nearer at the start. So dots were nearer. So the red line was nearer to all of the dots. Okay, so let us call this region as A, and then look at the extreme region. So here it is deviating, so the distance is higher. So it means in any all the individual dots are away from the red line, because the other lines are away. So let's call it B. So what is happening is, so if I draw the if I observe the variance between the if I draw the average value of distance from the red line with the crosses, the distance, so distance is for A, distance at A and B. So the distance at A is smaller. I will draw a bar chart, and at B is bigger. So the distance is actually variance, the model. So variance is actually defining the the errors in estimation, because it's a distance from the cross with, so it is actually y minus y bar, y hat minus y bar and whole square. So and this is actually used to calculate the r square and f test. So but the problem is, so if you split the sample into two, so let's take a different color. Let's take orange. If I split this sample into two groups like this, and I will name them. So it is uh, before some time, and this is after some time. So this line is some time or some value of leverage. So let's call it L bar, leverage bar. So you can notice is that when I have separated the data into two groups, I came to know that the variance in both models are not same. Why? Because you can see the average distance is nearer and average distance is far. So even though it was one good model, it was very good fit. But when I separated into two groups, the distance it's smaller at the start and larger at the second portion. So it means there are two sub models existing here. So that submodel is actually causing what? It is causing the change in the variance in the model. And it was actually assumed earlier that for OLS, the variance for each value of x must be constant. What does it mean? That is that if I draw a graph of error term square, which is a indicator for variance. So let's take error term square here. So why we take error term square as a variance? So we already know the formula for variance is x minus x bar whole square divided by n. Okay, and it's a summation here. Okay, so this is a formula for variance, and we already know E bar is 0. So what we do is, so E minus E bar whole square over n. So rather than do this, we say E square. So because E square is so E bar is 0, so E square is only portion here which is changing. So rather than calculating the variance as a number, so if we solve this, we get the RMSE if I take under root here. So it will be a constant. So rather than we calculate a constant, we calculate a data which is error term square and see how it behaves as compared to x. So when x is increasing, ideally the error term should be straight line like this, and its upper limit and lower limit should be horizontal. So the property of straight line is, we have already discussed, and it is being taught in mathematics, that if a graph has a straight line, it means the value of y-axis, so value of y-axis does not depend on x. So any value that you see, its y-axis does not depend upon x because it is not changing because of x. So it means E square is independent of x. So x is not causing E square. So this means that the variance is not changing in the model. But so this is the assumption that is required. But the case that I presented earlier, that is showing us that if the dependent variable has some subgroups which is theoretically performing differently with each other as compared to each other, what will happen? You are actually estimating aggregate model, but in reality there are some sub models which we need to cater. So the topic that we're discussing is models for heteroskedasticity. So the objective of this chapter is to explore what is the problem of heteroskedasticity that we discussed right now, and what are its sources. So we'll go towards these sources, and then we'll discuss what are the approaches that we can use to counter this problem. Okay, so major issue that led to heteroscedasticity is there is a quotation by Sherlock Holmes that never theorize before you have data. And invariably you will end up twisting facts to suit the theories instead of theories to suit the facts. So actually, theories are there to let me write it here so that you can understand what this quotation means. So theories are there for generalization. So to give one word or one liner synthesis of what is happening in the world. So that's why we make theories to try to shorten the explanation that is required to explain what is happening in the reality. That's why we make a theory. Just like we say growth theory. Growth theory is explaining how economic growth is happening. Or we can say the pecking order theory in finance, or any theory that you already discussed in finance. So the theory is a word or a sentence that actually tries to explain the what is happening with simplest possible way. So it is a generalization of reality. But what problem is that reality is complicated. So when we generalize the model, it doesn't mean that it is actually it's a wrong interpretation. It is actually giving us the one answer, which is represented by the answer represented by what you call it majority. That we discussed is that it is actually mean value or median or mod. So theory is actually average behavior or average pattern or average quality which we express. But the problem is if there are many subgroups, when you go towards the policy implication, the results might not help in most cases because there are packets within a data that are performing differently. So what Sherlock Holmes want to say is that you have to look at the facts first and then find theories that are related to it. So maybe you end up fitting more than one theory to explain the facts because facts are pointing towards subgroups. So if there are subgroups, so each subgroup might have a different theory. So that's why rather than thinking from the theory, you should look at the data first. So econometrics or data science, what they try to say is that first of all, when you are trying to go for a work, you should get a data. You should have some descriptive statistics that you did in the previous activity, or you can look at in the previous videos that how to describe the data. And so when you describe the data, you will find some hints that the data has some subgroups. So this is what we try to start. So if there are subgroups, there are there is a reason to believe that your answer might be actually correct, but when you look at any observation, it might not be correct. Okay, so let's start with. So heteroskedasticity is described as a situation prevailing in the estimated results. So it's a situation, not a problem. It's a situation which makes the variance of the model. And how we measure it? We measure it from residuals to become non-constant. So actually, this definition is what it is telling us what that it is a situation, and and how it is checked that it makes the variance of the model or variance of the residual not constant. So It means when you estimate an OLS model and if you plot a residual square versus independent variable plot, you will notice that there are patterns. And if there are patterns, it means there is heteroskedasticity. Okay. So there are some. So this is because of the construction of data or because of the nature of the variable. So there are many reasons for this study. This here we are talking about few of the popular reasons, and I will try to give reasons for all of them. So first reason, the most some popular reasons are following. Okay. So let's move forward. Let's see what are the problems. So first of the is that the problem of heteroscedasticity is maybe because the units or scale of the dependent variable and independent variable might mismatch. So you are estimating a model where the units or scale of the data are not matching with each other. So such that their change inherently causes variance to switch gears. So what does it mean? Such that in cases that we use transformation of data. So let's go back to the whiteboard and I will give you this example and then we'll come back to this point again. Let me share the whiteboard. So the problem number one is black color. So mismatch of units or scale. So let's take an example. So we say that and your GPA explains your wages in the market. Okay, so it means wage is a function of GPA. So we try to estimate this model that the more intelligent students tend to have higher wages. So logically, this is correct. So intelligent students tend to have good jobs and they tend to have higher wages, even though the reason might be not because of the GPA, there might be any other reason. So here we take GPA and here we take salary. Now let's simplify the problem. So let me take the different color. So what is the range of this wage data? It can start from 0 to maybe 4 lakhs, depending upon how. I am not talking about that it's a current student, it can be any old student. So uh, wage and 4 lakhs. So the range is 4 lakhs or what you call it 0.4 million. Okay, so this data is very wide. Okay, and the GPA that you saw here is what's its range 0 to 4. It is very narrow. So if you try to estimate what will happen, what regression will try to do is, so your dependent variable has, suppose this is this much wide, or I made it in terms of height, and you try to say that this height is because of some alpha plus beta and this height. Okay, so the dependent independent variable has very narrow height as compared to independent variable. What you have to do is to estimate this model. You have to enlarge it so that you try to estimate. So how you will enlarge it? You will have to make beta value bigger. Okay, so to estimate this model, you will notice that the W is equal to alpha plus 100 or 10,000 GPA. You tend to see this big slope coefficient. And if you show it to your teacher, he says, how the slope can be this big? Slopes are usually between minus 10 to 10. So they are not very big. It should be in between. So why it is 10,000? It is so big. So what is happening is that your wage data is varying very highly and your dependent variable is varying very slow narrowly. So slope tends to be very big. So if I make slope here, so 1 GPA leads to 10,000 units increase in salary. So it's a guess, the number might be bigger. So but problem is when you add more variables, it has very small beta. Maybe you end up add age as a variable. So age is also wide enough. more wider than the GPA. It might have a coefficient of 50. Okay, and some other variables it might. So what is happening is there is an imbalance between coefficients. When there is an imbalance, it leads to um, is it leads to changing in the variation of the model when the values are changing. So it might lead to heteroskedasticity. Okay, so let me give you a reverse example, and then so this is for the units. Let me give you a reverse example. Suppose we say that the income of family is explaining GPA. That more the family is rich, the better schooling that the children got, and because of that he has better learning and he has got a good GPA. So we try to estimate this model. So GPA is equal to alpha plus beta income of family. Now we'll try to estimate its range. So we find out that GPA is 0 to 4 and income of the family can be 0 to 5 lakh. It can be any value. So I'm assuming it's 5 lakhs, so 0.5 million. So what is happening is that now if you try to estimate this model, your dependent variable is narrow, is alpha plus beta, and independent variable is very wide. So when you try to estimate what regression will have to do is it have to shrink the independent variable to a smaller scale. So what will happen? The beta will tend to be very small. So it would be like GPA is equal to alpha plus 0.0000001 income of family. So this is very small. Your teacher might say why it is very small, and you don't have any answer because you don't know why software is giving us this number. So when you have different scales, different units, you end up having imbalanced coefficients, and it might also lead to heteroskedasticity because because of that what will happen that you will never know, you might say that my theory is correct and there is no problem in the sample, there are no subgroups, but still there is heteroskedasticity. So what should we do? So here what we notice is that it's not because of your mistake, it is because of the construction of the data. Similarly, for the case of the scales, let's say scale. So suppose you say you are estimating a perception survey. So your dependent variable is Likert scale. So dv is alpha plus beta iv. So dv is from 0 to 1 to 5. So uh, um, definitely not, and definitely yes, and there are 2 is probably not, 3 is neutral, 4 is probably yes. So it's a 5 scale data, but your independent variable is 0 and 1, means high. It can be anything, high versus low. Okay, so what is happening is same thing is happening, that your range the beta will try to adjust the range, and it will lead to imbalance coefficients, and that imbalance coefficients, what will happen, it will lead to uh, the regression will try to adjust them, and it's written here that where it is. So it's one step up. Go ahead. So what will happen is the regression will have to create gears. So that switching gears will lead to heteroskedasticity. So this is one of the reasons that explain the presence of heteroskedasticity, and we already studied how to check if there is a heteroskedasticity. So best thing can be that we can transform the data set. So common method is we take natural log. So the data which are wider or longer, we take natural log. So what happens is it converts the data into uh, growth rate. So even though the data is wide, the growth rates are narrow. And even if the data is narrow, it can have a high growth rate, because growth rate is actually percentage change. So it converts the data into, let me write here, it converts the data into the natural law. What it will do is it converts the data into percentages, which is relative form. So from that we can solve the problem. So this is the first of the problem that we where that might lead to heteroskedasticity. Okay. So the second point is that the hetero could also come from another source, that can be the intercept of certain slope the variable might change within the sample. So what is happening is that this is the example that I did for the banks earlier, that your sample subsample might have different slope or different intercept value. Okay, so it might lead to because of the change in environment. It could be an indicator of use of dummy variable for intercepts, or moderator approach for slopes. Okay, so let me give an example, then I'll come back to next point. Okay, so let me bring the white screen. So suppose you have estimated a model that we have a y-axis and then there is x-axis, x and y. So let me call it that study hours and GPA. Okay, so we already know that this model is positively sloped. The more you study, tend to have higher uh, higher GPA. But when you explore this model in detail, what you notice is that everything that is not discussed here is here in the intercept value. It's a starting point. Everything that you have not covered in this model. So, but the problem is that all the students that you have included in the sample might have two subgroups. One is smart students and others not smart. So what will happen is, if you separate them into two groups, you will notice that for the case of smart students, the intercept is somewhere here. So alpha plus, and for not smart is alpha minus. So within the sample, what is happening is, we know that the study hours will increase GPA, but for let's interpret. So for any particular studied sample value, smart students tend to have higher GPA. So y hat value, and this is y hat value for y hat minus and y hat plus. So what is happening is that if your sample has subgroups which is changing the variables which are not in the model, what will happen that technically you have, if there are two subgroups, there are two intercepts, but you are only, but if you estimate single model, what will happen is the regression will run an average model. An average model will be in the center like this. So I will name it average model, and this is not smart model, and this is smart model. So what will happen is that actually the model intercept is changing, but you are not changing it. So it will have heteroskedasticity in the model, because there is a variation in the data. So maybe now you notice that there is no increase in gap or decrease in gap. So how can we observe heteroskedasticity in this case? Because the lines are not diverging. But for the case of banks, the lines were going away. Here, the hetero could come because the not smart students are also studying less hours, because they think that it's not necessary for us to study more because we don't have any capacity. And the smart students are studying more hours because they are studying extra rather than the syllabus. So what is happening is, technically the data, the green line is good for whole sample, but when you look at the subsample, green line is not good for the start and also not good for the end. So what will happen when you draw the error term chart with respect to x? So let me label it. So we have x and array term square. So initially the variance will be bit lower, or as we call it, it's negative values. So and later on it will increase like this. It will have a jump. So it means that, and if you draw it as an average, it will show it like this. So what is happening is, there's a change in the variance because of x. So this is the reason of heteroskedasticity in the model. So I hope this is clear now for the case of intercept. So let's go towards the case of slope. So let's say that, okay. So let's say that here it is study hours, and there is GPA, and you estimated this model which is positively sloped, and this is actually good generalization of the theory. But the problem is that students who's who are actually uh, uh, consulting their the students who are studying in as a group, and they are seriously studying, what happening is, when they study more they tend to have higher GPA rather than the other case. So it will start from the same point, because study, let me label it first. So study with group and without group. So the intercept value is same because all other variables are similar. So what it is showing is that at particular study hours, a student who is studying alone tend to have this much GPA. Let's call it YA, and the student who is studying in a group tend to have higher GPA. Why? Because they are studying together, so they cover more syllabus by discussion and synthesizing the write up and summarizing it together. So what is happening is that in the reality, if you do not add this quality in the model, so regression will give us an average. So let me take a different color. So average model will be where? It will be in the middle. So let's start. It will give us this. So let's label it, it's average. So what is happening is the gap is increasing. So this is an example of the banks that I showed earlier. So what is happening is the dots that are there in the reality are very nearer to the line in the start, because the gap between both lines is similar. But when you look at the data, the gap between dots are increasing. So they are spreading wider. So what is happening? So there is increase in variance. So let's, if I draw it here, this is y-axis and x-axis, and so click it. So we have independent variable, which is x, and error term square. So it looks like it is positively slope, because as x is increasing, study hours are increasing, the gap between the student without group and with group is increasing. So it means the gap between the this average line and the red line, and the average line and the green line is increasing. So data is spreading with each other. So if I look at like this, the gap is like this much here, but this much here. So gap is increasing. So error term is positively sloped. So this is another example of hetero in the model, and we call it slope changing or slope changing situation. Okay, so let me give a solution here, then we'll move forward. So what should we do? So we have two problems. Let me separate the screen here. And the first problem we have here, we have, and the second problem here. So what do we do is that we have an x variable and a y variable and an x variable. So in this example, what was happening was there are parallel lines. In this example, we have spreading lines. So in the first case, what is happening is alpha is changing. In second case, beta is changing. What should we do? In this case, originally you have estimated y is equal to alpha plus beta x, and you notice that the dots are actually changing gear. And how you noticed? When you plot a scatter plot, you notice that initially they were lower, and after a certain point they jumped a bit, or vice versa. They were higher earlier and jumped down, came down a bit. So it means that there is, after a certain value of x, there is a change in gear. So change in nature. So it means what you have to do is you have to add another variable here, plus beta 0 and beta 1, and that will be a dummy or maybe a quality variable. So we can call it, if it is a student example, so dummy will be equal to 0 for not smart student, and d is equal to 1 for smart student. And how we can measure if they are smart or not? There are many ways. We can either take their entry test marks, we can either take their previous studies, or we can either measure from their, what you call it, IQ test. So we can make a dummy variable. What will happen is that the quality the quality which is causing a change in intercept value is, which was not in the model, now it is in the model. So it will solve the problem. So sometimes heteroskedasticity is solved by adding a variable that is actually changing the uh, intercept. So that's why you notice in the finance studies they always tend to add ln TA, log of total assets. Why? Because it captures the size effect. Or they sometimes take ln sales, which captures the size effect or volume effect, because the countries are different. And in macroeconomics, if the dependent variable is not GDP, they tend to take GDP as independent variable. Why? Because it captures the income effect or the size effect of the country. So this way, this means that sometimes hetero is there because you ignore one of the important variable that is causing the problem. Okay, so we have found this problem. Secondly, in this case, for the slope changing, so first of all we write the equation. So y is equal to alpha plus beta x. Here you notice that with the increase in x, there is something that is also increasing. So it means that the effect is also depending upon what is the value of x. So let me summarize it here. So the differences in the both lines are also depending upon what is the value of x. So it means there is some other quality, there is some other factor z is playing a role, but that z also depend upon value of x. So the effect, let me write it below, effect of other quality, other variable is depending on value of x. So what does it say is that actually z is there to affect the line, but the bigger the value of x, the bigger the value of x, so bigger the contribution of Z. So it means both are together creating an effect. So I will write it here is it is beta 1 x multiplied by Z. So you notice that y-axis is multiplied because it is actually they are jointly contributing to what is effect. So this way we control the slope changing point, and in theory it is called as moderator model. A moderator model is a model which tries to capture the slope changing effect of other variables which were not in the model, and you try to add them and you control the slope changing pattern. Okay, so this way you can control the moderator. And in our I will do one activity where we talk about the difference in this how the line will change if the value of d or z changes. So we'll do that activity later on. But here I talked about how to solve this problem. So if you have an hetero, you have to notice that if it is slope based, so your residual will have a jump, and if it is intercept based, the residual will have a jump. If it is a slope based, the residual will have an angle. Clear? So hopefully this way you will identify which is the source of the problem and what is a possible solution. Okay, let me go back to the. Okay, then the point C is for discrete dummy variables, if the qualities are interrelated, it could lead to heteroskedasticity. What does it mean is that suppose you already know that it is the case when the independent variables are inverse. Suppose if there are two qualities and both are opposite to each other, so what will happen is if one is there, other is not there, and the for case of other, so they are inverse of each other. So what will happen is the error term one time will be higher, another time will be lower. So this way, whenever you use a dummy variable, it will it will lead to heteroskedasticity. But it can be properly solved is by if you properly constitute the dummy variable, or you can create more cases, like you can expand the data by using a panel data. Okay, the point similarly point D is in some cases your dependent variable is qualitative, discrete, or categorical. Okay, so means your dependent variable is binomial 0 1, or it can be multinomial for two or three cases, or it can be truncated, means it has an upper and lower limit, or it can be a continuous, or it can be a discrete variable. Discrete variable mean it cannot go into points like number of people injured, number of people killed in an incident, number of attacks by terrorists, number of crimes reported. These are the variables which are discrete, but they are quantitative. So what will happen in this case? You cannot use linear approximation. What OLS does, the OLS assumes that the dependent variable is continuous and quantitative. So, but here they are not. So it will lead to heteroskedasticity. So for that, there are alternative models available, and we will study them one by one in this chapter. Okay, lastly, there is a frequency mismatch. If there is a frequency mismatch, there's or there is a regime change in the sample. Frequency mismatch means that one of the data is quarterly and other of the data is annually. So even if you transform the data, what will happen is that it will not give us similar results. So because if there is a frequency mismatch, so you convert the annual. Suppose your dependent variable is quarterly, and your independent variable is in annual form. If you convert the quarterly data into annual form to so that your frequencies are homogeneous, what will happen? Most of the information in the quarterly data will be lost. Okay, and and it will not give appropriate results. In other case, suppose you try to convert the annual data into quarterly data, it will be artificial approach, and it will not give us the actual nature of the data, and it will lead to heteroskedasticity. So these are few popular reasons that that may lead us for heteroskedastic estimates. Okay, so let's move forward. So it is talking about that the more details are discussed in Gujarati book, and it's chapter number 15. Let's